Hello everyone, this is Tejasvi Tumala. Today I am going to discuss about the Illumination Models. Photorealism. Photorealism is the art of style to convey objects or characters and scenes to look as real as possible. Artist basically takes the pictures of real objects and textures them how the original object looks like. It is mainly used in gaming field. These photorealism games take more time to create as every object is made up of pixels. Also, photorealism takes up more disk space. That's why some games appear to come up to as 2 to 3 disks. The picture here shows the image of an photorealism, which is textured from the original object. Light sources. Light sources are termed as light emitting sources. It is basically an optical transmitter which is paired with an optical receiver, both of which are connected to electrically based systems. So the source converts electrons to photons and the detector converts photons to electrons. There are various kinds of light sources such as point light source, parallel light source, area light source. Point light sources emits lights equally in all the directions from a single point, whereas the parallel light source emits light rays parallelly, that is, the rays hit planar surface at identical incidence angles. Maybe this parallel source can be modeled as a point light source at infinity. It is also called as directional light source. The good example for this parallel source would be sun rays. Area source. Light that originates at finite area in space. It lies in between the point and parallel light sources. It is also known as distributed light source. Coming to near and far light sources, if a light source is placed nearer to the object, then it is known as nearer light source, whereas a light source placed far away from the object is known as far away light source. Intensity attenuation. As light moves away from a light source, its intensity decreases gradually. It decreases by a factor 1 by d square. But usually this 1 by d square does not produce good results. Therefore, in order to produce more realistic effects, inverse quadratic function is used. The function which is shown here is inverse quadratic function, which is used in calculating the intensity attenuation factor. The coefficients A0, A1, A2 can be varied in order to produce optimal results. Basically, this intensity attenuation is not applied to light sources which are placed at infinity. Spotlights. Spotlight is a light source which illuminates in the form of a cone. It is similar to a directional light, but it has defined volume in the shape of cone in which the light falls. The amount of the scene that is illuminated depends upon the angle of the cone. These spotlights usually have drop-off rate. It is basically the degree to which the light nearer the edge of the cone becomes less brighter compared to the center. A good example of spotlight is torch beam, in which the light ahead directly is the brightest point, while to the either side of the light becomes dimmer usually until there is very little illumination. In the figures shown below, the figure on the left, the landscape is illuminated by a single white spotlight, positioned left of the screen and pointing downwards to the right. The light has a moderately wide cone of effect, but no drop-off rate is specified here. So the edges of the light cone are just as bright as the center of the light cone. Whereas the figure on the right shows the effect of multiple lights in a scene. But here the landscape includes red spotlight which emits red light, a green point light positioned as above, and a blue directional light aimed towards far left of the screen. The combined effect of all these multiple lights looks a little stranger here. Angular attenuation. As we move far away from a light source, intensity of light decreases angularly also. The below expression is used for calculating the angular attenuation. It is cos power A1 phi. Here the angular attenuation exponent A1 is assigned some positive values and the angle is measured from the cone axis. Flaps and cones. In order to restrict the effect of light to limited area, these flaps and cones were introduced. Flaps are usually confined to the effect of light with coordinates of x, y and z. Each light will have 6 flaps which will correspond to the user specified minimum and maximum values in each coordinate. Also, these flaps will have a flag which indicates whether it is turned on or off. When a point's shape is determined, the illusion model is evaluated for the light of which the point coordinates are within the range specified by minimum and maximum coordinates. The figure below shows an example of x and z flaps when light is parallel to y-axis. And the figure on right shows the cone with a generating angle of gamma, which is used to restrict the light sources. Illumination models. First of all, let us discuss about the color of an object. Color is basically the property of light that depends on wavelength. When light falls on object, some of it is absorbed and some of it will be reflected. The apparent color of opaque object depends on wavelength of light that it reflects. For example, a red object observed in daylight appears only red because it reflects only the waves producing red light. Whereas the color of transparent object is determined by wavelength of light transmitted by it. The image shown here shows here the in the presence of red light, the apple appears to be red color because it reflects only the red light, but the leaves of the apple look black light because it doesn't reflect any color other than red. In the second figure, in the presence of green light, the apple appears to be black because no red light strikes it, but the leaves look green. In the third figure, the apple appears in the presence of the blue light. Both the apple and leaves appear to be blacker. Now coming to the surface lightning effects. When a light is incident on opaque surface, part of it will be reflected and part of it will be absorbed. The amount of the incident light that is reflected by a surface depends on the type of the material. A shiny materials usually reflect more of the incident light, whereas the dull surfaces usually absorb more of the incident light. Whereas for the transparent surfaces, some of the incident light will be reflected and some will be transmitted to the material. The illusion model basically computes the lightning effects for a surface using various optical properties such as surface texture, degree of transparency, color, reflectance. Now coming to the diffuse and specular reflections. When light is incident on rough surface, the incident light scatters the reflected light in all the directions. This light is known as diffuse reflection. In addition to the diffuse reflection, some of the reflected light will be concentrated into a highlight or a bright spot. This is called as specular reflection. In the figure shown here, the instant light diffuses in all the directions. This is known as diffuse reflection, whereas the instant light reflects in a particular specular direction. This is known as specular reflection. This highlighting effect of specular reflection is more pronounced on shiny surfaces compared to the dull surfaces. Now coming to ambient light. This is basically a non-directional light source. The intensity of the ambient light is constant and it is not affected by anything else in the world. The amount of ambient light incident on each object is constant for all the surfaces and over all the directions. Therefore, this is a simple way to model the combination of light reflections from various surfaces to produce a uniform illumination called ambient light or the background light. Usually in this basic illumination model, we set the general level of brightness for a scene. In the example shown here, we can see the ambient light, which is a background light, diffuse light and a specular light. And the fourth figure shows the combined effect of all the ambient light, diffuse and specular light, which has the effect of the background light, the highlighted spot and also the uniform illumination of diffusion light. Now coming to Lambert's cosine law. Lambert's cosine law basically states that the intensity observed from the diffusely reflecting surface is directly proportional to the cosine of the angle between the direction of incident light and the normal surface. Surface which obeys Lambert's law are called Lambertian surfaces and exhibits Lambertian reflectance. Such a surface will have same radiance when viewed from any angle. It is independent of viewing direction. Now coming to ambient reflection model. As we have seen that the intensity is constant for the ambient light for any surface. The contribution of ambient light is given by the following equation, which is the product of IA and Ka. Here the Ia is ambient intensity, whereas the Ka is ambient reflection coefficient. Now let us see about diffuse reflection model. As against the ambient light, which is constant for all the surfaces, this diffuse reflection is constant over a particular surface. The amount of instant light that is diffusely reflected can be set up with a parameter called as Kd, which is diffuse reflection coefficient. This Kd is assigned a value between 0 and 1. For this Kd is assigned a value of 1 for highly reflective surfaces. This produces a bright surface with the intensity of reflected light near that of the instant light. To simulate a surface that absorbs most of the instant light, Kd is set to 0. The intensity of diffuse reflection at any point of the surface can be given using the expression here, which is the product of the diffuse reflection coefficient and ambient intensity of ambient light. Since diffuse reflections scatter in all directions with equal intensity, such surfaces are called as Lambertian reflectors, as the radiant energy from any point on the surface is governed by Lambert's cosine law. If theta is the angle between the incoming light direction and surface normal, then the area projected perpendicular to the light direction is proportional to cos theta. So the amount of incident light here will be given by IL cos theta. Here IL is the intensity of light source. Then the diffuse reflection for a point on surface will be given by Kd into the amount of incident light. Here where Kd is the diffuse reflection coefficient, as we have seen before. Now by substituting the instant light intensity, which we have discussed before, it will be Kd into IL cos theta. If the in the below figure, if L is the unit vector and N is the unit vector in the normal surface, then the dot product of N and L will be NL cos theta. As N and L are unit vectors, then the dot product will be equal to cos theta. Now the substituting this value of cos theta in the before expression which we have seen, the diffuse reflection will be given by an equation Kd IL into N dot L. Now when we combine the ambient and point light source intensity calculations, the total diffuse reflection intensity will be given by the combination of ambient light and the diffuse reflections intensity, which is KIA, which is the contribution of ambient light, and KD IL into N dot L, which is the contribution of diffuse reflections. Here the values of Ka and Kd depend on surface material properties, and usually these values are in the range of 0 to 1. Now let us see about the specular reflection model. We see a highlight or bright spot at certain viewing directions. This is called as specular reflection, which we have seen before. This is the result of total or near total reflection of incident light in a concentrated region around the specular reflection angle. In the figure shown here, the L is a unit vector which is directed towards the point light source, whereas R is a unit vector in the direction of ideal specular reflection. V is a unit vector pointing to the viewer from the surface position. The intensity of specular reflection is proportional to the angle between the viewing vector and specular reflection vector. Here ns is the specular reflection exponent, which is determined by the type of the surface. Usually shiny surfaces will have a larger values of ns almost equal to 100 or so, whereas the dull surfaces will have smaller values of ns almost around 0 or 1. Hence the intensity of specular reflection is given by the equation which is shown here, that is the product of Ks, which is specular reflection coefficient, into intensity of light and cos power ns phi. As in the figure shown in the previous slide, as V and R are the unit vectors, the dot product of VR will be equal to cos phi. Now substituting the value of cos phi in the above equation, the intensity of specular reflection can be modeled as the final equation shown here, which is product of Ks and intensity of light and the dot product of VR power ns. Now coming to the examples shown here, in the first figure we can see only ambient light, which is a background light which is constant for all the surfaces. In the second figure we can see the combination of ambient and diffuse reflections. In the third figure we can see ambient, diffuse and specular reflections, which is highlighted with the bright spots and everything. So we can see the difference of the combinations here. Now computation via the halfway vector. When a halfway vector is placed between the light source vector and the viewing position vector, we can model the specular reflection in an easier way. In order to model this halfway vector, the v dot r dot product in the specular reflection, which we have seen before, is placed with the dot product of n dot h. Then the halfway vector can be computed using the equation which is shown here. Multiple light sources. When we have more than one light source, then the light reflection at any surface point is obtained by summing the contributions from all the individual light sources. Hence, the equation here clearly shows that the intensity of all the light sources is given by ambient reflection plus the summing all the reflections from diffuse and specular reflections from different multiple sources. Here in the second equation we substitute the intensity values of all the ambient, diffuse and specular reflections which we have obtained from the previous discussions. Now coming to transparency. Some of the objects allow light to pass through them, and while the other objects do not allow the light to pass through them. Here the transparent objects allow light to pass through them, whereas the metal objects which are opaque do not allow the light to pass through them, whereas the translucent objects allow only part of the light to pass through them. Hence the glass which is shown in the first figure is a transparent object which allows the light to pass through them, and the contents of the object are clearly visible through it. Whereas the translucent object, the bottle which is plastic bottle which is shown in between, is a translucent object which allows only certain amount of light to pass through them. Therefore the contents of the plastic bottle are not clearly visible, but they are visible. Whereas the third figure here, the metal object is an opaque object. It does not allow any of the light to pass through it. Therefore the contents of the metal are not visible at all. Coming to Snell's law. Here, when a light is incident in a medium and it is refracted into another medium, when the medium of n2 is greater than n1, then the velocity of v2 is less than v1. The angle of reflection theta 2 is less than the angle of incidence theta 1. That is, the ray in higher index medium is closer to the normal. Then the Snell's law states the ratio of sines of the angle of incidence and refraction is equivalent to the ratio of the velocities in two different medium, which is also equal to the ratio of the wavelengths in that medium, and it is reciprocal to the ratio of the incidences of refraction. Now let us see about opacity. Opacity basically tells about how much an object is opaque. That is the degree to which the light is not allowed to travel through an object. It means if an image has lower opacity, then it means the image is more transparent. This property of opacity can be applied to multiple objects as well. Now coming to the shadows. Shadows are the areas which are hidden from the light source. That is, when we are viewing from the light source, certain areas are not visible. These areas are known as shadows, which can be clearly seen from the figure here. When the light is illuminated from the other direction, the areas which are in the black color cannot be seen. These are known as shadow areas. We can determine which surface sections cannot be seen from the light source by applying a hidden surface method with a light source at the view position. These are known as shadow areas. Once all the shadow areas are obtained, these could be treated as surface patterns and they can be stored in pattern arrays. Now coming to light intensities, perceived intensities. The amount of light we humans can experience is different from the amount of light measured. Humans can respond to very lower light levels, thereby allowing to enter more light into the eye. Therefore, there will be difference between perceived and measured light levels. Example, a light which is dimmed to 1% is perceived to be dimmed by 10%. The formula to calculate this perceived light is shown here. Now coming to gamma correction. When we want to display an image accurately on screen, gamma correction comes into picture. It controls the overall brightness of an image. Images which are not properly corrected can either be looked too dark or can be bleached out. This gamma correction can be defined using the power law expression which is given here, which is V out equal to some constant A into V in power gamma. Now let us look an example of this gamma correction. The effect of this gamma correction on an image shown here. Here when gamma equal to 1, we will have the original image. When we increase the power levels by higher in the higher levels by gamma equal to 2, we'll have a more darker image. When we decrease the powers to decrease the power levels, that is by decreasing the value of gamma to 1 by 2 or 1 by 3, we can have a little darker images. Required intensity levels for high quality viewing. The number of intensity levels depends on the image and what we would like to do with the image. The number of intensity levels used to represent an image is usually referred as intensity level resolution. This intensity level resolution is usually given by the number of bits used to store each intensity level. Usually the higher number of intensity levels we use, the more level of detail an image will have. Here the figure shows the number of bits required, the corresponding number of intensity levels required. Coming to halftone techniques, it is a reprographic technique that simulates continuous tone imagery through use of dots which varies either in size or space, thus generating a gradient like effect. That is, the halftone is an image which is which comprises of dots, and when a user or a person views from a certain distance, the dots blur together, creating the illusion of continuous lines and shapes. So by halftoning an image, it can be printed using less ink. Therefore, this halftoning is used to print more pages like newspapers or magazines very efficiently. Coming to the intensity of halftoning technique, the quality of halftone image depends on its resolution. The resolution is usually measured in terms of LPI, that is lines per inch, which is the number of lines of dots in 1 inch. Usually a halftone with high resolution will have greater detail than a halftone with lower resolution. There are different dot patterns. Usually we use round dots. Other than round dots, we have elliptical dots and square dots also. Round dots are most commonly used. These are used for light images. They usually meet at a tonal value of 70%. Whereas the elliptical dots are used in images which have more number of objects. Elliptical dots meet at a tonal value of 40%. There will be a more risky pattern in this elliptical dots. Coming to the square dots, it is best for detailed images. This is not recommended for skin tones. The corners meet at a tonal value of 50%. The transition between the different square dots can be sometimes visible to a human eye. Coming to the problems in dot patterns, usually one problem that we face with dot patterns is that the size of the dot will be growing as the ink is pushed onto the soft surface like a shirt or something like that. Usually the dot will grow up to a size of 25 to 35% when printed properly. If it is printed still poorly, it can grow to a size twice of its usual size. This means the print will be looking muddy, like with no details and all. The figure here which is shown here is a bit muddy and less detailed. Coming to dithering techniques, dithering is a technique which is used to create the illusion of the colors that we don't have by random arrangement of the pixels. In the image which we have shown here, the pixels are randomly arranged, white and black pixels are randomly arranged, and when they are arranged in a particular order, it can form into an other image. Now here the pixels are arranged and the figure we have obtained is shown in the next figure. Here the arrangement of pixels will be changed, but the quantity of pixels will not be changed. Finally, here we have obtained a black and white image by arranging the pixels separately. Dithering by halftone approximation. All the devices cannot display all the colors, therefore we use this dithering technique. That is, we provide the illusion of many colors with the available colors which we have. In this halftone approximation technique, we create metapixels by grouping the base pixels into 3x3 or 4x4 dither matrices. Here an example of 2x2 dither matrix for grayscale is shown. Similarly, a 3x3 and 4x4 dither matrices will be used in order to approximate this halftone image. Now coming to error diffusion. Error diffusion is also a kind of halftoning in which the quantization error is distributed to the neighboring pixels which are not processed, which are not yet processed. That means the error is pushed into unprocessed nearby pixels in order to make sure that the current percentage of black and white pixels are generated locally. This error diffusion uses an area operation because what the algorithm does at one location influences what the algorithm does at other locations. Therefore, a buffering technique is required here, which usually complicates a parallel processing. There are many kinds of error diffusion technique algorithms. Here we are discussing about Floyd-Steinberg dithering algorithm. Here in this matrix, the star indicates the current pixel that is being scanned, and raster scan is usually used here. The blank pixels are the ones which are already scanned, whereas the other pixels, the pixels which have the values are yet to be scanned. The algorithm scans the image from left to right and top to bottom and quantizes the pixel values one by one. Here a pseudo code for the error diffusion using the algorithm is shown here. For every pixel that we scan from top to bottom and from left to right, we will first take into consideration the existing pixel value, and we will now calculate the new pixel value. That is by using this function find closest palette color. The new pixel value is obtained by dividing the older pixel by 256 colors. 256 because we have 256 different colors. And now we'll calculate the quantization error, but that is by subtracting the newer pixel value from the older pixel value. Now all the rest of the pixel values are obtained by summing the older pixel value with the quantization error into the pixel value. It gives us the in this way we can diffuse the error into the nearby samples, and we can get the correct percentage of black and white pixels so that we can produce different shades with those that are not available also. So these are the differences which I have used in this presentation. Thank you.